All right, well, let's go ahead and get started. Welcome, everyone. My name is Chris Gaffney. I'm the Executive Director of Parkinson's Support and Wellness. We are an organization based in the greater Cincinnati, greater Dayton Metroplex. We provide services in the area of education, exercise, and support groups for persons with Parkinson's in about a 32-county area in southwest Ohio, southeast Indiana, and northern Kentucky. One of our primary missions is education, and throughout the year we have an educational seminar once a month. We call them PD EDUs, and we're kicking off this year with a very special presentation. Actually, we have two members of our board. Dr. Alberto Espay is our medical director. Maureen Gardner is our medical liaison, and she will be introducing Dr. Espay in just a moment. We've been going through some of the housekeeping, but just so that you know, everyone, your camera is off and you are muted. That's because we now have nearly 200 folks participating in this event this morning. Now, if you have any questions during the presentation and during our question and answer period later, you can place your question in the Q&A that you'll see an icon that has the opportunity to type out your question, and we will recognize you at that time. I want to let everybody know that we are recording this session, and we will edit out these first few minutes with the stuff that you don't want to hear and see. But that recording will be available on our website, Parkinson's Support and Wellness's website, which is parkinsoncincinnati.org. No S after Parkinson, so parkinsoncincinnati.org. And I would invite you to visit our website and take a look at the various programs and services that we provide. With that, I'll hand it off to Maureen Gardner. Most of you probably know her, but Maureen, if you'll get us started.
Thank you, Chris. So I have the pleasure of introducing Dr. Espay this morning. He and I have worked together for 18 years now. He's currently the director and endowed chair of the James and Joan Gardner Center for Parkinson's disease and movement disorders at the University of Cincinnati. He completed medical school in Venezuela, his internship at St. Vincent Hospital in Indianapolis, and his residency in neurology at the Indiana University School of Medicine. From there, he did a 2-year fellowship in Toronto with Dr. Tony Lang. And if any of you know about Dr. Lang, he's one of the most highly respected people in the movement disorder area. He's been noted in Best Doctors in America 6 years in a row. He has more publications and research than we have time for. I could never, ever talk about them. But what he does, the other thing he does have is a real passion for research. And it's not just research for science, it's research to help people deal better with movement disorders. And that's what his passion is, and he is all about it and does it well. So, Dr. Espay.
Thank you very much, Maureen. I appreciate that introduction very much. It's amazing to believe that we've been together for as long as 18 years here in Cincinnati. It is been a very important journey for all of us, and as you'll know very well, and hope our people hearing as well also, it is clearly one where we have changed quite a bit in terms of that thing we call Parkinson's disease. We, I think, have a very organized approach to saying to someone, based on our expertise, what you have is called Parkinson's disease. But that quaint approach to the diagnosis coined for the 19th century, most of the 20th, should not really apply to the 21st. It cannot be that I or anyone in my position recognize all that needs to be recognized to call someone, here's the disease you have, sorry I cannot prove it to you, but I'm an expert. So part of all of what you'll hear in a moment and what we'll discuss thereafter is from the recognition that we remain the last bastion of medicine, neurology, in particular neurology of diseases of brain aging, in which we continue to define diseases based on how they look to us. We observe, we ask questions, we take a history, we move people, we do the pull test, we ask them to do finger tapping, and then we say, this is what this is, based on our experience watching people, and as you learn, based on what it appears is on the proverbial ashes of the fire, the so-called autopsy, right? So that's sort of how we came to define this concept called Parkinson's disease. So what I like to do, and I think what I hope you'll find of interest, is to go over my recently released TED Talk, which is going to go over the foundations of this and how we came to think about Parkinson's disease. You got a bit of a taste of what's to come. And these are going to be 15 minutes. So it'll not be too long. That's all that's considered a lecture for today. And then we're going to end at that point and open the session for a conversation about the meaning of it, themes that are related but not touched upon at the TED Talk, and then what else is it that we are doing and proposing to do for understanding the approach to Parkinson's as a different type of precision medicine and rescue medicine approaches, which haven't been really so far deployed in our field as they have in other fields of medicine. So with that, I'm going to ask Julia and Chris to start then the TEDx presentation. And as soon as that finishes, I'll be here, and I hope that you'll all join me for a conversation on what that means and what we're doing from there. Enjoy. Everyone loves a story with the villain. It holds our attention and it galvanizes us against a common enemy. In the field of neurodegenerative diseases, which include Parkinson's, Alzheimer's, and others, the victim is the brain and the villain is the abnormal proteins. We have a name for it. We call it proteinopathies, diseases of the proteins. And we have, in fact, accrue a variety of strategies to get rid of this criminal, to take it out of the brain of people that are suffering from neurodegenerative diseases. And despite how well we've done this, we haven't really been able to get much out of that effort. So we've come out empty-handed, and it is time to rethink the narrative about the extent to which brain aging is accelerated by these abnormal proteins. It may be that it is not about how much of these villains we have, these abnormal proteins, but rather how few of the normal proteins we have left. Before we delve into the research that is helping us define what might be the most promising of all interventions, let me back up a bit. I'm a neurologist. I study diseases of brain aging. How do I diagnose conditions such as Parkinson's or Alzheimer's? I do it by asking questions and observing patients. I looked at individuals in terms of how they move, how they talk, how they behave. For instance, if someone is slow, has a tremor in one hand, might shuffle a foot when walking, I would say you have Parkinson's disease. I can't prove it until I have a biopsy or an autopsy, but trust me, I am an expert. And I'm applying criteria that my expert forebears developed a while ago. So how do I really get away with this? How do we neurologists get away with just disclosing a diagnosis in a manner that requires trust? Well, it all began in the early 1900s when our forebears had only one major technology at their disposal, a microscope. And what they did is that they used it on brain tissue of people who had died of impairment progressively in terms of memory, what we perhaps now today call most often Alzheimer's, or people who had progressive slowness and other abnormalities in what we today call Parkinson's. And what they did is that they applied the microscopic techniques, as primitive as they may have been, and when you are doing that, as you can imagine, positioning yourselves in their eyes, they would see on the brain things that look like this, these abnormal clumps, wads of protein. And they looked abnormal, and they looked like they shouldn't be there. So the part of the narrative that began at that point was in assuming that what they had encountered was the cause of the problem. That somehow, as the brain had these kinds of proteins there, that it was the evidence that in fact gave rise to the abnormalities, to the degenerations that ultimately created the problems for which the patients died. But are they really the villains? And let me explain how they in fact came to be. Normal proteins are, in fact, looking rather like this. As you can see, they are so flexible and light, they can fall off the table. But as you can see, what they ultimately are is so flexible and soluble, that means dissolvable, that they can perform functions. It's dissolved in water. The solubility of it allows us to quantify it in the liquid that surrounds the brain, and that we can measure that through a spinal tap. These proteins are all over the brain. They are, in fact, so critical that the genes that code for them have been preserved since prehistoric genomes, and that explains why they are all over the brain. They are critical for the brain's structure and ultimately to keep the neurons communicating one with another. But what happens when we encounter in the brain something that shouldn't be there? Something that might be a virus, for instance. Well, these proteins then have something that will be the source for what we call a protein transformation. From soluble, they clumped into these very compact wads, and very similar to what you saw earlier. And ultimately, more of them accumulate, as you can see here. And what happens, therefore, is that the normal proteins are becoming less and less common, less and less in concentration, but the source of the problem becomes invisible. And what we end up with is a lot of this, ultimately. As you can imagine, the normal proteins are now absolutely gone. The aspect of this story that is important to realize is at the end very simple, and that is that proteins are only able to function when they are normal, when they are in this soluble functional state. That the minute they clump into something that they aren't normally in, they no longer function. And the process is universal across all neurodegenerative diseases. It really is one in which when we ultimately see the transformation of these proteins into the clumps, those proteins are ultimately so compact, so tight, that they are almost impossible to be toxic. This is not unlike milk. Milk is ultimately, if we leave it outside of the refrigerator, it's going to go bad. It's undergoing a soluble to insoluble phase transformation, and that is ultimately what will make the milk curd. Now, you can imagine trying to dissolve the curd, but you cannot imagine bringing that curd back to normal milk. You will never drink it. The paradox that has been greatest in our field is that we have been remarkably successful in eliminating this protein from the brain. We've had the best part of 2 decades testing anti-protein treatments in the amyloid, the synuclein, and more recently another protein called tau, and the tau proteins. And if you think of the field of amyloids, for instance, there have been over 40 trials testing approximately 20 interventions that clear up the amyloid from the brain, and 75% of these trials have shown that the reduction in this, so if you just imagine that this is kind of coming down, the brain is getting clean, it's been so successful that you would think that if they are the villains somehow, then our brains should return to normal and people should get back to state of normalcy. Not only has that not happened, but in 40% of the trials, those who were allocated to the experimental arm had the greatest reduction of amyloid worsened. And in many cases, their brains shrunk further. This is a problem. We should be able to look at the data and falsify a hypothesis when the hypothesis fails to be confirmed in clinical trials. So, at this point, we wish to resolve the paradox in the literature, and what we've done is we've studied 600 people who already had plenty of amyloid in their brains. We can measure the amyloid in the brains by using something called a PET scan, and ask the question of what is the difference between people who have these abnormal clumps in their brains and remain normal versus people who have it but are already demented. And we found that the difference is how much of this there's still in the brain. So we actually can have plenty of them, and we've actually now observed that it doesn't matter how much of this there is in the brain. If the levels of the normal protein are high, that individual will be normal. So the story and the narrative about where we are in terms of our development holds on to the narrative that these proteins are toxic. And it is not unlike thinking that a forest ravaged by a storm somehow would be restored back to health by simply cleaning up the broken up trees, right? Reforestation will be needed there, but just taking all the debris won't. So the story is as follows. We now have an enemy that we think of as necessary and sufficient for the development of diseases, and in fact, it isn't. If it were, all of us having these in our brains would have diseases of the brain, and most of us don't, as we've seen. Furthermore, if these were the toxic elements in the brain, and we were able to remove them, as we've done, then those who had a removal would be back to health. And that is also not the case. But there is a better way ahead, one that actually thinks about the elements of the story. So rather than insisting that these proteins aggregate and the accumulation of the chunks of abnormal protein are actually going to create the difficulties in the brain, we now have an opportunity, and perhaps in our toolbox of future therapies, to increase the levels in the brain such that it doesn't matter how much of this we may already have. If we increase the levels of the proteins in the brain, we can in fact get to levels where the brain can operate relatively normal. Now, the way we're doing this is based on a couple of important developments. The first is that the peptides are coming into a brain that's obviously fighting against something. We don't know what that is. This part remains invisible in research. We're saying if you have Parkinson's, trust me, it's a disease. If you have Alzheimer's, trust me, it's a disease. It isn't. It is a syndrome, right? So this is going to be the source of precision medicine. But if we are able to bring the brain, the levels of these normal proteins, to elevate the levels to normal, then it won't matter if we don't yet know what that is. Now, the proteins would have a transformation that prevents them from turning into itself, right? So that hinge that makes that clump appear would be changed, but the rest of the protein remains normal. We have now demonstrated that above a certain threshold, and the threshold is now well defined, patients can be rescued. So precision medicine will require us to get to this, and this is an individualized approach, but rescue medicine would allow us to, in fact, use the opportunity to bring back what the brain is losing in the process of neurodegeneration. I'm working with a number of scientists very interested in moving us into this. We're no longer testing the effects of removing the chunks of was. We're beginning, in fact, to test how to bring this to people affected with Parkinson's, Alzheimer's, and other conditions. And as a neurologist, I can tell you I have never been more hopeful. Thank you.
Building your business online.
All right.
Well, Dr. Espay, I think your last word was maybe the most exciting. Hopeful.
Yeah.
It's what so many of us who are dealing with these diseases need so desperately. That was exciting. Please carry on. And I'll remind everyone, you can place your questions in the Q&A, and we'll be monitoring for those questions as they come up.
Thank you very much, Chris. I appreciate the opportunity again. What I'll propose is for maybe Maureen or Julia to field the questions as they come, and then we'll, of course, tackle them as they come. So I see one already. What's the name of the peptide that is the villain? The peptide is another name for a protein, a collection of amino acids. The most important peptide or protein in Parkinson's is called alpha-synuclein. And alpha-synuclein is very important, is all over the brain, precisely because it is critical for a brain to react against a variety of exposures. As we age, the more that we're exposed to, the more opportunities there may be for diseases of the brain. And synuclein, alpha-synuclein in particular, can be very important. Now, when it fights against something, it transforms from its normal soluble state, that's dissolved in water, that's why it's called soluble, into an insoluble state called the Lewy bodies. The Lewy bodies we have held as the villain in this story, and that's why in this TED Talk I'm trying to make the case it isn't the villain. It is not the cause of the problem, it is the consequence of the problem. So when you chase a tail, you get nothing. That's why we have 2 trials already published for anti-synuclein antibodies, and they are negative because that approach can't work. It's not like, oh, if we have more patients, if we do a larger study, if we get the dose to be increased, if we change the experimental paradigm, none of that will matter, because the problem is not that we're not doing enough of what we're doing, is that we are doing something that isn't backed up by the evidence that we now have. And so while the story that we created about these peptides, these proteins being toxic, had a lot of logic when it was first conceived, ideas in science are false until proven otherwise. And we have not been able to prove them otherwise. It doesn't matter how much of the Lewy bodies our brains have, as I alluded to in the presentation, it doesn't correlate with shrinking of the brain. It doesn't correlate with the kinds of symptoms people have. And therefore, the Lewy bodies cannot be the villains in the story. They are indeed the victims. So I hope that that concept came through. That's the most important concept of this presentation, because all of you are going to hear about new trials of anti-synuclein therapies, and we cannot continue doing them. Now, when I say we, I mean all of us. But it turns out that we, when I say neurologists, so people like me, we have a conflict of interest. It's an unfortunate one to admit, because a conflict of interest is that these trials are very, very lucrative to institutions. And so that has been one disincentive to move away from these trials, because they bring income to institutions like ours. Fortunately, the University of Cincinnati is not pushing us into taking these studies simply because they are lucrative. They recognize that we also assess the value of them to our patients. And because we know there is no value to our patients, and in fact, much potential harm, we don't do them. So I hope that answered that question appropriately. Maureen, do you want me to go through it? Did you have been looking into which questions? I am delighted that there is a lot of questions already pouring in. This is exactly what I wanted.
So there's a couple questions, Alberto, about how do we increase the good proteins or the peptides?
Yes, so that is going to require a what's called an analog or a peptide analog, which is essentially replicating the same string of amino acids that make this particular protein called alpha-synuclein. It's a string of 140 amino acids put together, but changing a part of the protein exactly the point in which it's acting as a hinge. So you saw this in the presentation. I actually brought another example of this. You saw this, and what happens is that there is a hinge around which then the protein begins to turn into what you then end up seeing as this in the presentation, right? That is no longer functioning. That's not a functioning protein. Our narrative, this is the villain, this is replicating, spreading, propagating. No, this is just simply becoming the result of the normal protein. So how do we increase it? We increase it by creating an analog of this. This is the exact same thing as our brain makes, but it's only modified in a part of it that acts as the hinge around which then the folding occurs, that transformation occurs. We're working on this now. We've been working on this for the last year and a half or so. We are expecting an acceleration of this because the Michael D. Fox is reviewing a research program on this, and also because I have colleagues at the Karolinska Institute that are far smarter than I am and have very important resources in the preclinical state. This is trying to determine really how much the proteins added on to a model can in fact rescue the model. how it makes sure that it's not toxic. And then we have to define such things as what's the best route of administration, how much it gets to the brain, how much it stays in the brain, how long this stays functional, right? Because that defines how often replacement therapies will have to occur and so forth. So, so we are probably thinking that we're about 2 to, I hope not 3. I think it's going to be under 3 years before we can make the shift to humans. With the interest in these ideas, it is possible that there will be more interest and that perhaps more funding will come from companies or foundations to help this be accelerated. But we're very excited because it only makes sense, and investigators in China have actually learned of our studies in humans and decided to do a model that applies mostly to Alzheimer's, but it's exactly the same principle. They gave 2 models of Alzheimer's that have clumps instead of Lewy bodies. They're called amyloid plaques, and they gave him more of the stuff. They created the one that's not modified. So of course you have to then replenish more frequently, because in a brain that is under stress, then this quickly becomes this, and you don't want that. So they have already replicated a rescue. So the principle is actually relatively simple. I think of it as Occam's razor. Is really the easiest and most straightforward explanation for what happens to the proteins and what we can do for them. So not too long from now, we're going to have more data, but I'm expecting that within a 3-year interval, we'll be able to begin testing this in a phase 1 study in humans with Parkinson's disease.
There's a couple questions. Is this related at all to dopamine and levodopa production?
Yes, to the extent indirectly, the proteins that we have aren't directly themselves making the neurotransmitters, but these are in many ways the soil on which the neurons that grow, and they are the ones that create the neurotransmitters, is where they are. So this is sort of a way to keep those neurons healthy. If you have not much of this, the lower the levels, the sicker the brain is, then the neurons cannot generate the dopamine that we know is deficient in Parkinson's. So what we are doing with therapies currently, and we've been doing it for 50 years, is replenishing the levels of the dopamine using levodopa, because that's what the brain makes, and what the brain isn't making enough of. Therefore, the dopamine production is low, but we need to go upstream. And one level upstream is precisely giving the brain what is missing, which is the proteins that are being transformed into Lewy bodies. Of course, the ultimate approach, as I mentioned, is to be able to get to a point where we address the cause of the problem. These proteins are transformed into Lewy bodies because something is triggering that transformation. We call it something is catalyzing this transformation. It's a nucleation process. And so I talked about milk, for instance. That's one example of that transformation from normal milk to curd. It happens in nature in general, from water to ice, from water to liquid. This is a phase transformation. So that is very important to target, because it doesn't require to know what is causing it. Now, what's causing that, though, that's the source of precision medicine. So we have rescue medicine, which is the addition of these proteins into the brain that are being depleted, that we can then rescue because we can bring those levels above the compensation threshold. And then that is a universal approach that can apply to most people, if not all. Precision medicine is an individualized approach. Precision medicine is to answer the question, why Jim's Parkinson's appeared, and how is Jim's Parkinson's different to Mary's, and how is Mary's different from George, and et cetera, right? That is what we're doing in the biomarker program of aging called the CCBP in Cincinnati. And that's the highest level of medicine. That's what happens in oncology, where somebody is being told you have a specific cancer, let's say breast cancer or prostate cancer or liver cancer. And the doctor immediately says, but we don't know what that means. We have to do this test, this other thing. And then and only then we know what to treat, because then and only then we know what disease you actually have. We skip all of that in our approach to Parkinson's and Alzheimer's and other diseases of brain aging. We simply say, this is your disease because I say so, because I'm an expert. And so that's the highest level. So we have symptomatic therapies, which is what we've been doing for 50 years, trying to replenish the neurotransmitters that are not being produced enough. We can go to rescue therapy, which is what the TED Talk was all about, to trying to add the proteins that are becoming depleted, regardless of what the cause is. And that's going to be a likely powerful universal approach to this condition. And then we have precision medicine at the pinnacle, which is actually really just very much finding the needles in a haystack, trying to find out why each of our patients is unique. We've said no two patients are alike, but we've not done the research acting as if we mean it. Now we are, but that's of course a much longer term program, although one that we have a strategy to be able to begin deploying, begin harnessing the successes of it before the decade is over.
So with that precision medicine, do you foresee a new patient getting a spinal tap to determine levels of normal and villain proteins?
For now, I do. However, there are ongoing efforts to being able to measure the levels of the protein in blood. And it's a very tricky situation because it's hard to find what about the blood levels of anything represent the brain levels of anything. But it's something called exosomes. They're kind of like nanoparticles that come from the brain and are able to be measured in blood with very sophisticated newer techniques. So in the future, we may not need to do a spinal tap to measure these levels. For now, we do. And we're, in fact, in one important study that is being undertaken in individuals who have synuclein duplication, a genetic mutation in the synuclein gene. We're measuring those levels in the spinal fluid because we're determining in those individuals what is the threshold for compensation, because they will likely be the first beneficiaries of a synuclein replacement strategy.
Okay. There was a good question here. Can you help us understand the relative mass of the good proteins versus the clumped proteins against the mass inside the skull? Is it a significant percentage or a tiny portion?
I like that question because that question is so interesting. So I'm gonna say that every story has two sides, right? Now in Parkinson's, we've used only one side of the story, which is the side of the clump proteins, right? They go up. And when you don't particularly think of where that comes from and just look at it, of course, is bad. Now, if something goes up, eventually you would imagine, as it probably is the specific tone of this question, that the brain's going to run out of space, it's going to have too much of it. But in fact, the brain is not having more. Neurodegeneration is actually a problem of loss. In Parkinson's, the loss is not that clear on imaging, but there is a little change in the brain volume going down. So how it comes that this stuff goes up, and the brain is going down? That makes no sense. Well, it's not that this goes up, it's that the measurable fraction of the protein, which actually can only, in its normal state, can only be measured in the spinal fluid, once it gets accrued into a clump, we just measure it. Now, when it wasn't there, the levels was 0. When now we can measure it, and now so far in Parkinson's, we cannot use a PET scan. We can only wait until somebody's brain tissue is available, which of course is an autopsy procedure, to measure how much of this is in the brain. Now, the fraction is high, but it's not that the levels of the proteins are high, and that's important concept. It's not like proteins are growing. This is not a cancer. This is still a loss. And the proteins in a total extent are becoming depleted. We're losing proteins. We're just measuring most of that. So in a one-sided story, we can only say that essentially this is going up, right? That's bad. But what happens is that the levels of the proteins are going down, going up. Now you have two sides of the story, one side that goes up, the other that goes down. In a process of degeneration, what goes down is much more important. What goes up may be reactive or in some cases even protective. And what goes up, as I mentioned, is really a relative term. It goes up in relationship to the fact that we cannot measure this in a normal state. So I think that's.
So is there any intervention in breaking that up? Breaking up those clumps?
Yeah. So no, we already have accomplished this. And so we're really great at getting rid of this stuff. Biotechnology has delivered products and therapies that already are doing that. And there are, of the 72 trials in the pipeline for disease modification in Parkinson's disease, a full 2/3, so 63% or so, are all therapies that now are we're testing them in humans with Parkinson's that clean these up. So we're really good at doing that. I'm arguing that cleaning this up leads to nothing good, that this is not but a sign of the problem, not the source of the problem, that the source of the problem is something we don't really know what it is. In my TED talk, I use this particular thing, just something like a little ball like this, and I say, this is different in different people. This is what creates a problem, but it's mostly invisible. Now, this is what makes proteins fold up, right? Let's say that this could be a virus. It's very well demonstrated that herpes simplex virus type 1 can actually get, if not treated, can do this, can get the proteins to clump up, form this, right? So that will be a cause of the problem. But in most cases, this is absent. So essentially, what we're dealing with is the loss of the protein, the accrual of the fraction of this. So it looks like this is going up, but really it isn't. So I hope that the answer to the question that you just posed is, yes, we've been this is a one-sided story. This is going up, and we have many therapies for this. Now, recently, there have been 2 trials that were just reported a few months ago in the New England Journal of Medicine, which is the most important journal in medicine. And there were 2 anti-synuclein trials that cleaned this up from the brain. And in both cases, there was no change. It was futile. In our narrative, we felt that these trials weren't good enough, that the dosage must have been something that perhaps needs to be worked on, that the measurements we took were not sensitive enough, and our favorite excuse is that the patients were already too advanced because they have symptoms. Imagine if our oncology colleagues would have come to any of their negative trials and say, well, no, we knew that this would have cured the cancer, but the reason this trial was negative is because the trial was imperfect. We need to do the same trial, different molecules, just keep on doing the same approach until we finally get a result. No, oncology and other fields of medicine use negative trials to reject their hypothesis. We do not reject hypotheses because we feel that they are perfect. And of course, we've all grown up with the idea that this is the bad thing. The Lewy bodies are the villain in the story. And so, yes, we already have been able to do this, but no, we are not able to take that evidence and saying, all right, well, the hypothesis is incorrect. We need to reject it. We somehow cannot do it. So my pledge to you all is that if you're invited to any study of disease modification, if it's going to be anti-synuclein, please say no. It's not going to work. You have at best a chance of not being harmed, and at worst, you're going to be harmed. It's definitely no way can be beneficial. There is just no way, right? It's again in the analogy of the milk. It's like a trial that is going to clean up the curd, but you're not going to drink that milk. You're not going to drink the milk. So that's sort of where that comes from. Any trial that's currently disease modification should also ask the question, why me? right? Disease modification, as I mentioned, is a precision medicine principle where a therapy is to be matched to the biology of an individual. So if you have a therapy that does something spectacular in animal models, the disease is destroyed, the animals are recovered, you have to find out what about that therapy is applicable to you. So when you're invited to a trial and the investigator say, here I have something that's going to slow the progression of your disease, the question you need to ask is, all right, why me? And if the answer is because you have early Parkinson's disease, that's the wrong answer. The correct answer should be because this intervention acts by this specific mechanism of action, and the biology that we've been able to determine about your condition is one that renders you suitable to benefit from this therapy as a candidate for this particular trial. Oh, that will be the greatest explanation for why you should participate. Otherwise, do not participate in those kinds of trials. They are going to lead nowhere. Now, for now, there are many trials for symptomatic enhancements. Yes, those are important for us to continue participating in, because there is so much more that we can do to try to continue bringing therapies to help with the symptoms. But until we get it right in terms of disease modification, which is a completely different animal compared to symptomatic therapies, we should really not be continuing to just fit into those trials. And actually, unless patients say, enough, I'm not going to be doing this, we're going to continue doing them. So there is a lot of power in patients, and I hope that you'll exercise them.
So if you replace these peptides, will that replace dopamine?
So if you replace these peptides, you will nurture these fragile neurons back to health, and those neurons will then be able to produce the dopamine and produce the other neurotransmitters beyond dopamine that are associated with Parkinson's. So dopamine is very important for motor function, but there is norepinephrine for other functions, autonomic functions. There is serotonin also affected for emotional function, et cetera, et cetera. So the proteins will just get the conditions for it's kind of like reforestation. It's allowing the neurons to then remain healthy. And then those neurons are the ones that are going to make all these different neurotransmitters, including dopamine.
So there's a question about LRRK2, and I have to go back and find it. LRRK2 shows mitochondrial fission. How about reversing that?
Type 2 mitochondrial function?
LRRK2 shows mitochondrial fission. Is there a way to reverse that?
No, and I'm not sure that I'm not sure actually even what mitochondrial fission actually means in this context. LRRK2 as a gene, when mutated, create an increase in the kinase function, which apparently is what's neurotoxic to it. However, so LRRK2 generates a very wide range of potential presentations, one of which is classic Parkinson's, but it can generate all sorts of different things, many of which we don't even call Parkinson's. Some of them are called frontotemporal dementia. Some of them are called progressive supranuclear palsy. So the Parkinson's gene that LRRK2 represents is actually not very clean. And then the penetrance, that is the extent to which it will actually express, is about 30%. So most people with LRRK2 mutations don't ever develop Parkinson's. Now, because this is so diverse, because one gene is not equal to one disease, one gene can still give rise to many expressions of disease, each of which are biologically different. One approach will not work for them, particularly to address for instance, the kinase inhibitors, which are the drugs used for LRRK2, are unlikely to work because they are chasing likely a common denominator of what the gene expression is. And common denominators tend not to be the cause of the problem, but rather the consequence of the problem. So here, though, rescue with proteins could work because we don't need to necessarily understand at an individual level how LRRK2 is creating the brand of Parkinson's in the particular individual, but the protein elevation will help. So the proteins will work here, but it can work in other people without LRRK2 just the same.
And do you think that there's any lifestyle changes that can increase the peptides? And
Yes,
what
yes, I'm
impact
gonna say,
would that have?
that's a great question. And just I noticed that the question you asked me, I actually saw that, and the first statement was of that particular question, lecanemab showed great efficacy with Alzheimer's. How do you account for that? I don't want to miss that question because that's an important question. Lecanemab is a drug that the FDA recently approved for the treatment of Alzheimer's, and it's medication that actually cleans up amyloid from the brain, so it gets rid of the clumps of proteins, not called Lewy bodies, they're called amyloid plaques, but the principle is the same. So how it comes that lecanemab is potentially efficacious. Now, by the way, the measure of efficacy is statistically significant, but not clinically relevant. It's in a scale of 0 to 18. This is 0.45, so it's less than a half a point. 1 point, and in some studies, 2 points are required for the minimal difference that any patient can tell a difference on. So this falls below the resolution of what anyone can tell. Patients are still deteriorating. But what makes lecanemab potentially of use, even though it's very harmful, because 1 out of 4 patients actually get sicker with it. It develops brain swelling, etc. So it's a toxic thing to the brain. But why is it that there seems to be at the end a margin of difference that favors for the first time a drug that has lowered this? Because this is not the first one. There have been 15 other antibodies that have done the same thing, have really very substantially eliminated this from the brain. He said actually it increases in some people the levels of the normal proteins. This thing goes up. Now, because that's not part of the expected outcomes, the investigators have relegated this very important piece of information to the supplementary material of the New England Journal of Medicine article where this lecanemab study was published. They mentioned nothing about it in the paper whatsoever, and you find this information that this goes up there. So my hypothesis, and I've hoped that Eisai and Biogen, the sponsors of this trial, would actually get back to their data and find out if, in fact, those who benefit are precisely the ones that end up increasing their levels of the normal protein above the compensation threshold that we've defined already. I don't know if they're going to take us up on that offer, but that is an important question, and they have the data to ask this particular question. As to the one that you just asked me, is there anything that can be done to increase the levels of the normal protein? It's a great question. Turns out, yes. And it's something I discovered recently. You may have all heard of the ketogenic diet. Ketogenic diet is essentially a diet that is aimed at decreasing the processed carbohydrates as much as possible. So very, very low carbohydrates, and all the diet based on protein and fat. So it's kind of like a modified Atkins diet. And the idea is that that will minimize the relative concentration of glucose, which is not the best sugar in a brain under stress, whereas ketones is. Ketone is a much more useful and more efficient source of energy to brain under stress. Well, it turns out that one of the things that ketogenic diet does, and it's been demonstrated a couple of years ago, but it was just brought to my attention recently, publications have shown that the levels of the normal protein actually also go up. And so that is fascinating, because that might explain why people do get better. It's just a very hard diet to do. And we are thinking already through a way of making a modified diet, perhaps amplifying the ketogenesis by including in the diet a ketogenic supplement. So I think that's very interesting, because if that can be accomplished, as you can imagine, that will be much better than any infusion system, right? It would be a matter of ensuring that the dietary aspects to it are adhered to in the most strict way, just so that then this can happen. But yeah, so that's kind of interesting, and I think that that could be one way in which you could all accomplish this. We did a study of ketogenic diet, and it was very hard to do because, admittedly, patients find it difficult. It's a difficult diet to be, but if you can do it. And maybe if you can not do it as stringently as we did it when Robert Krikorian, our investigator here at the University of Cincinnati, led it, maybe with addition of a ketogenic supplement, that could achieve enough of a ketogenesis to potentially drive the levels up. Now, we don't know if that is also going to get us with higher levels of the normal protein, but it could be. And so that's a fascinating question, and I hope that we can answer it more definitively in the next couple of years.
And why does exercise slow the progression of Parkinson's disease? Why do we stress that so much?
So exercise is the only intervention that is multifaceted, meaning it doesn't do one thing. It does all sorts of different things. And it ends up having an impact on the mitochondrial metabolism, in the lysosomal function, in the inflammatory response, etc. It has all sorts of things. Now, what's interesting about exercise is it, in addition of being just a very wide range of biological changes, is that it tailors the changes to the individual. So that if you have two individuals doing the exact same type of exercise, frequency, intensity, those two individuals will get different benefits. They will benefit, but the underlying biological drivers of the benefits will be individualized. No therapy can do that we have. And so that's why we think of exercise as truly the only disease modifying intervention we now have access to. And that's why it's so important. That's why we stress it so heavily in each one of our visits, because that's the one treatment that maybe all of us have been hoping to get into a capsule, but we cannot, because this is what is really true precision medicine in some level, right? It's adapting biological changes to the individuals that are doing the exercise. We don't have a capsule that can be so adaptable, and probably never will. So we have to recognize that exercise is the one thing that all of us cannot do without.
And has the recent research revealed anything about genetic versus environmental factors that lead to Parkinson's disease, and which might be more of a factor?
Okay, so I hope that by this point in our discussion, you know that when we say Parkinson's disease, we don't mean here, this is Parkinson's disease. Everybody's different. And so, yes, individually, each of us have a genetic set of vulnerabilities and an environmental set of exposures that combine to create the brand of Parkinson's we develop. But what genetic and environmental exposures may apply to me would be very different to just about everyone else. And so so the answer is yes, we know that at a population level there are all these very many different things that happen, right? Exposure to pesticides, exposure to well water, increasing the risk, exposure to smoking, decreasing the risk, and also. But so we created a bit of a what investigators have called the puzzle of Parkinson's disease, where it seems as if we just are very, very close to finding the last couple of pieces to the puzzle of Parkinson's disease, so that we'll understand Parkinson's exactly as it is. And that's hubris. So we've gotten to a point where we know so much about Parkinson's, the disease construct, and so little about how Jim's Parkinson's came to be, how Mary's Parkinson's came to be, how George's Parkinson's, right? We know so little about that. And so I'm now very mindful when questions like that come over. It says, well, yeah, we have a population-based assessment of risks, some risks that are increasing the risk of Parkinson's, exposures that are decreasing the risks of Parkinson's. But how many of them apply to you, if any? We don't know. For now, I think it's important to emphasize a healthy lifestyle is largely good, but it's so interesting that it's not exclusively good, right? So as I told you, smoking, coffee, and red wine are good. And you would argue, well, those are surrogate markers of not the best possible life. So I don't know if that's correct.
I'm all about the red wine. Come on.
Thank you. We need to defend the red wine. So I think that each of us is just an individual, and we should not continue on the idea that here there is more studies to be done to learn about Parkinson's disease. I'm no longer that interested in studies to advance our knowledge in Parkinson's disease. I want to find out what about each individual affected with Parkinson's is important to that individual. In the past, we would say, please, John, come into my study. You have Parkinson's, and the more we study about you, the more we learn about you, the more we'll learn about Parkinson's disease. I don't think that's the right approach. We've been doing that for so long that you would think by now we would have figured this thing out. If Parkinson's were one disease, we would have conquered, but it isn't. It isn't one disease. I wish it were, because it would be easier to some extent. It's going to be hard, but we just have to make the change. It is unavoidable. Other fields of medicine have done it. That's why cancer was never cured. But look at the progress done on individuals affected by cancer because they were looked upon as individuals, not upon how is it that they fit into this model of cancer.
So, to kind of wrap this up, Alberto, there's, as you stated in the beginning, there's so many other neurodegenerative diseases besides Parkinsonisms and Alzheimer's. There's a little question on essential tremor, but it also leads me to think about it, when precision medicine comes about, it's going to target, hopefully, all these degenerative diseases, right? Hopefully prion, hopefully CJD, hopefully frontotemporal dementias, right?
Yeah.
Maybe even essential tremor, because we don't know how essential tremor starts.
Absolutely. Absolutely. I think many of the labels that were used have made a lot of sense to us. We created these boxes, and in other fields of medicine, they also created their boxes, but then technologies came and then they were available for us to question those boxes. And that's what other fields of medicine did. We don't do that. We said, hey, that guy, James Parkinson, in 1817, when he first described 6 people with what he called the shaking palsy, wasn't to something. And we're about to prove that he was out to demonstrate a molecular biological construct. No, he was very astute for his time. He was able to pick a few features that were common across 6 different individuals, 3 off the street and 3 that he saw in his clinic. And then Charcot, many years later, said, "Hey, Parkinson's wasn't to something. Let's call this Parkinson's disease." Now we have technologies to be able to question all of these concepts. And in fact, that's why I've written the book Brain Fables, because in that book, I just go through all the different milestones that led us to where we are. Very important, compelling, logical stories that when you look at the data from which they come, they don't support what we're saying. We're just having all these technologies that we could have used to question that which we're calling in the matter we're calling. And we have not changed. So all these terms, as you're mentioning, Maureen, essential tremor, frontotemporal dementia, dementia with Lewy bodies, all of them are clinical pathologic constructs. We created them because we figure, hey, look at the people, look what the symptoms they have, and let's see what the autopsy shows. And then we make sense of them sometimes because, oh, well, in retrospect, because of this autopsy, all these symptoms must have been due to what we see in the autopsy. And I find that this is just a primitive way of practicing medicine anymore. It made a lot of sense, but it doesn't anymore. How often do you come to the scene of a crime in a forensic setting, and what you see and what jumps at you is the perpetrator of the crime? It's almost never. You get evidence to create a narrative about the crime, but you rarely uncover the perpetrator just on what you see. It gives you clues to try to figure that out, but it's not from what you see. And yet, in our forensic approach to Parkinson's, which still dominates to today, we continue to use the forensics to tell us what caused the problem, which are the arsonists. And that is just an incredibly alluring but biologically false story.
And just one more quick idea to throw out there, because there's been a couple questions. What do you think about the stem cell approach to increasing the good proteins?
So a stem cell approach is an interesting approach that is falling under the category of neural restoration. So it is kind of like rescue, but not quite there, because rescue approach we've talked about here is going to sort of lift all boats, so to speak. Stem cell therapy can lift one or two boats at a time, because in stem cell therapy, you're replenishing a group of neurons or cells that would do something specific. You cannot replenish, you cannot do a stem cell therapy to the different regions of the brain that are affected, only the region. So stem cell therapy is currently in Parkinson's being developed for replenishing the therapies that make out dopamine. That could be good, but we don't know how much more effective yet it will be, if at all, compared to, say, deep brain stimulation, or compared to, say, the newer dopamine infusion system. So these cells could be good. They could avoid the need for infusion systems, but they might not. We don't know yet, but they can only replenish a specific region of the brain. And that's what makes it tricky so far. But I'm very interested in stem cell therapy, though. I think that there is something there that we would need to understand better. I just think that the scope of it at the moment is not going to be quite as critical, as widely encompassing as we think it might be. The idea sounds better than the practicalities of it.
Well, as Chris said, and I don't know if you want to wrap it up, Chris, but my takeaway from this is always, as I always tell my patients, there's hope. There is absolutely hope, and we can never give up, because we will always find some other way to help you.